is changing the fastest? What is it in terms of the picture? It is the point where what happens? We change from being concave down to being concave up, or vice versa, right? So when I look at this graph, would you agree that the first part of the picture is concave down?
Yeah.
But the middle part of the picture appears to be, or excuse me, the first part is concave up. The middle part of the picture is concave down, and then it becomes concave up again. So clearly it changes, okay? Where does it change? Well, finding the exact point is a calculus problem, but kind of just looking at it, doesn't it seem like your point of inflection would be -1, -1, or very close to that, and then 1, -1? Okay, so is everybody clear on that? Those would be the points of inflection, where we go from being concave up to down, or back again. All right, now for each of the following intervals, determine if the rate of change is increasing or decreasing. Now, we need to get straight in our minds. If we want to know if the curve f of x is increasing, we simply look at its slope. But what if we want to know about the rate of change? Then we must look at concavity. So when you look at the interval on your picture from 3 to 4, from where x is 3 to where x is 4, is that part of the curve concave up or concave down? Up. So what is the answer to the question? Is the rate of change increasing or decreasing? Increasing. Concave up is increasing. Guys, this is such a simple concept. I don't know if we're overthinking it. I don't know really what's going through your mind. This is a simple one. We'll do one more. What about from -4 to -3? -4 to -3. Those are x values. Look at that part of the graph. It's increasing because the rate of change is increasing, because isn't that part concave up too?
Yep.
Yeah.
Now, the curve itself is decreasing. You can be decreasing and concave up. Isn't that what's happening right here? But concave up means your rate of change is increasing. Okay, now I want you to go to the back of the next page. The back of the next page. I don't know if we did this or not. I don't think we did this page, so I'm going to do it now. Did we already do this? The back of the next page looks like this. Okay, check your understanding. Selected values of a polynomial function are given. Determine the degree of the polynomial. Okay, let's make sure we know how to do this. So, I don't know, there's something about these sideways tables that bug me, so I'm writing mine this way. Doesn't matter one single bit, because I write it the way you want. Looks like I'm going to need a calculator here. Now, what am I going to do? First of all, I'm going to notice what is happening to my input values. They're same size. Critical piece, they're same size, okay? So now I'm going to come over here and I'm going to start finding these differences. Would you agree with me? All right, so let's do that real quick. Help me out here. This is going to be -40. This is going to be -8. This is going to be 72. Keep an eye on my arithmetic. Okay, I don't know, are those numbers right, I hope? Okay, what conclusion can I make at this point? It is not linear. It's not first degree. It's not linear, it's not first degree. Okay, so now I'm gonna find my second differences. So I'm gonna do the same thing going this way. Good grief. Are those numbers right? Okay, well then it's not quadratic, it's not second degree. So I'm moving to the third differences. Those look okay to everybody? Oh shoot, I'm about a numbers here. I hope this works. So your question was, determine the degree of the polynomial. What's the degree of the polynomial? Fourth degree. Fourth degree. Whatever differences match. So first differences match, it's linear. Second differences match, it's quadratic. As long as the input values have the same size intervals. Okay? You cannot use the differences if the input values do not have the same size intervals.
What would you do if like they didn't match, like you did?
Then you would not be able to draw a conclusion based on the information that's given. Okay? Now, you always have the option, I mean, assuming you have the option, of putting these points in and doing a regression to see, does it fit a cubic regression? Does it fit a quartered regression? But you can't do it this way unless these are the same size. Okay? Because we're using just the differences. Okay. The graph of a quartic polynomial is shown, quartic degree 4. How many x-intercepts does that picture have? How many x-intercepts? 3. Now, be careful. Negative 2 has multiplicity 2. Would you agree with me?
Yes.
And then we have 1 and we have 3. So even though you said to me there's 3 x-intercepts, there are truly 4 zeros, which is important because they told me it's a quartic polynomial. All right. Determine the number of relative minima and label them. Minima means low point. Relative means the lowest point in that part of the graph. Okay, so look at the little chunk of the graph, what's the lowest point in there? Well, in the first, I'll say on the left side of that picture, what is your relative minimum? It happened, your relative minimum, you have one at -2, where x is -2 or the point -2, 0. So sometimes they say at x equals. So this happens at x equals -2, the point is -2, 0, and that's what you would label.
So the answer would have to be a ordered pair.
In this case, I think so. Are there any more relative minima in this picture? Yes.
Yep.
And it would be approximately where? So 2 comma negative, well, maybe 2 point something. So 2.1 comma negative 3.4. Someone from Litchfield, Illinois is calling me. Hanging that up right now. Okay. All right, so is that it for relative minimum? Okay. Now, relative maximum. So a maximum in a particular interval. Now we gotta be careful because sometimes we count the endpoints and sometimes we don't. And it depends on whether we think the curve is continuing or not. When I look at this picture, there's no dots to end that picture. The grid just ran out, so we stopped drawing. I'm thinking this thing's going on forever and ever. So those are not relative maximums. The only relative maximum we have is at 0, or maybe, I can't tell, is it maybe negative 0.1, comma, 2.5? Something like that. We're approximating. I'm not getting all bent out of shape about that. That's approximately where it is. Now, if, we put dots here to indicate this is it, this is the whole picture, then that could be considered a relative minimum, or relative maximum. Because in this part of the graph, it is the highest point. But in this case, the implication is it goes on forever and ever. All right, how many times does the graph change concavity? It starts out being concave up. And then what happens? It becomes concave down, and then what happens? How many times does it change concavity? 3 times. Label the absolute minimum A, or explain why this value does not exist. Isn't this point right here the absolute minimum? Label the absolute maximum B, or explain why this value does not exist. There is no absolute maximum because why? What's going to be your explanation? Both sides of the curve extend to infinity. A polynomial G has x-intercepts at 0 and 4. So think about what that means. I mean, you touch here and here. Which of the following statements must be true? Does it have to be a quadratic? Couldn't it look like this, folks? Is that a quadratic? No. So could it be a quadratic? Yes, but it doesn't have to be. G must change concavity on 0 to 4. Does it have to change concavity in this interval? Does this change concavity in that interval? No, that's not true. G has an absolute maximum or minimum at 2. Now the way I drew it is kind of deceptive. There's 2. Does that high point there have to be at 2? No. So it must be D. Does there have to be a relative maximum or minimum on the interval from 1 to 4? Yes, because in a polynomial, if you have a dot here and here, they must be connected. And they're never connected with a straight line. So it's either going to bump up somehow or it's going to bump down somehow. And that automatically means there's going to be a maximum or minimum depending on which one it is. Does that make sense to everybody? Okay. Now, I'm going to give you back I want your pencils put away. I want all your pencils put away, out of your hot little hands. Pencils put away. All right, so I'm going to give you your quizzes back. I want you to look at them. Okay? Daniel Michael, perfect paper. Your Michael, new paper, you know. Now, here's what I want want you to do, what I need to know from you is, many of you got bad scores because on the free response part, you did not show me any work. You are smart. You figured out the right answers. Most of you, almost everybody had the right answers, which is good, but there was no work shown. If you have your work shown, you don't have any pencils out there, no pencils in our hands. If you have your work shown somewhere, I want to look at it, and I will consider giving you some points back. So if you have that, I need to talk, you need to come see me. And otherwise, you need to figure out what in the heck you were thinking when you made some of the mistakes that you made. Okay. Does anybody have work to show me? Okay, Ellen, bring it on up. I'm almost done handing out books to you. Yes. Now, guys, listen. When we do this AP type work, if you are provided with an answer sheet, which you will be in every AP test you take in every subject, you must put all of your work, anything you want graded, has got to go on the answer sheet, because they do not look at the test booklet. Only the answer sheet gets graded. So your work must go on the answer sheet. So Ellen has her work here. And I have to check, I don't sure that's right.
Got it.
Okay, so Ellen's gonna give you back those, how many things
But the rate of change is increasing. But if it's
You have
negative or positive,
This is
increasing and decreasing in the rate of change.
This is the answer sheet. See how it says answer question on this page? So all that needs to be shown here. All that needs to be shown here.
I mixed that up on the entire test.
This is correct here. All right, anybody else have the answer?
So you said if you
Okay, so boys and girls, if you have work somewhere, I need to see it, okay? I need to see your work if you have work somewhere, and I'm going to adjust your test score or quiz score. But I need to see it.
You would get 4 or 11
You still missed one. Anybody else?
I'm not sure.
Yo, Daniel, is the answer to 11 and 4? 11 and 4.
My grade was I just make stuff that's good. Alright, so in cases,
Why not like that?
and then, but if it's just like the function itself, if it just says increasing or decreasing, then that's like, but for the rate of change, that is okay. So if it says rate of change, it's
Alright, anybody else have work shown for those previous spots in a different place on the test?
Is the rate of change, and that's. Oh, that's so annoying. Stupid terms that like, there's so many skills that you have to memorize. So constant means, all the same number. One word, one word, one word.
I just thought it was
All the ones I didn't get wrong are the ones where it's like decreasing at a decreasing rate. All the other ones are, and then you stop. So weird. With it.
yeah, I was rate of change. And then what would agree?
Hey, you know what? I know. I was like, where are you going?
Okay, so I tried to like
Alright, couple more minutes, and then we're gonna get started with our,
because now this is the rate of is linear because these these are increasing linear, but these are not constant, they're not the same number. This was don't understand it. I was like, I just make it so frustrating. Because like if it was linear, then be linear. Yeah, it's weird. Linear doesn't mean the line is
okay,
so you're
do you have everybody's papers unless I already have yours? I have yours, I have.
Like that's just so like I literally had to write
okay, so
that's like
Yeah, negative.
get that one wrong already. And I was like, she sounded so different when she answered that question.
Negative and increasing.
I was like, I'm doing something wrong, I just don't know what.
I don't even know why.
So, it's just like,
Alrighty,
come in during office hours during that.
absolutely, you can come in during office hours any day to do anything you want. Alright, do I have all the papers back again? Okay, and I will adjust the scores for those of you who gave them to me. Alright, so now we're moving on. Oops, somebody's pencil's on the floor. Bryce, you are going to hand out these papers, make sure everybody has one. I'm gonna hand out these. And we are going to continue the conversations we've been having.
It's on my book. This is all one chapter. Oh my god.
Okay, did everybody get a paper from me and a paper from Bryce? So you should have gotten a big packet and a little packet. I want everybody to get the homework packet out for just a second, then we're gonna put it away. But I have another correction to make. Someday I'm gonna start doing the papers before I run them off. I need you to find, by the way, some of you didn't make the last correction I did, so that's why you missed the problems, because you didn't make the corrections. Next time, I'm gonna take points off your homework. I'm telling you, you need to make a change. Go to the new homework that Bryce just handed out. Go to the 1.8, the 1.8, and that picture at the bottom, here's the change. In the picture, there is an asymptote at 1, and there is an asymptote at -3. And then there's another asymptote across here. And then there's this parabola-ish. It's not really a parabola, but it's that shape. And it should be approaching this asymptote. I have it approaching the y-axis just because I was careless. It needs to scooch that over, redraw that line, so it's approaching that asymptote. All right, so the picture needs to be corrected so that what was going up along the axis is actually now going up along that asymptote. Everybody got that fixed? Oh, grab one right there. Okay? All right, here we go. That's our correction. We got it made. Now we are looking at our notes in 1.6. Much of this we've already talked about. These topics in chapter 1 just kind of all flow together. Or not chapter 1, unit 1. Here we go. The end behavior of a function describes how a function behaves as it moves infinitely to the right and left. We talked about this already. If a polynomial function has even degree, what is its end behavior? Above, positive infinity, positive infinity. Unless we put a negative in it and then it's negative infinity, right? That's what we mean by end behavior. In other words, the end behavior is what happens to the values of y as x increases or decreases without bound. Now, the notation we are going to use for this is our regular calculus notation. I do not know what you used last year, and I don't care. We're using regular calculus notation, so I want you to look at example 1. When I look at example 1, I am going to describe the end behavior like this. This is my notation for end behavior. This says the limit of the function as x approaches negative infinity is what? So take a look at that picture. Where is x approaching negative infinity? Over here, right? So as x goes this way, as x approaches negative infinity, what is happening to your y? Positive infinity. So on the left side of the picture, this is the left side of the picture, the curve is shooting up. So where it says left behavior limit statement, this is it. What is the verbal? The verbal is what I said. As x decreases without bound, as x goes left, 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 decreases without bound, y increases without bound. As x goes negative, y goes more and more positive. Okay, now what happens on the other side of the picture? Now, look, x is approaching positive infinity. That's right, that's that way. So as x goes to positive infinity, what happens to my function? it is doing what? Going down. When you write your limit notation, we might as well make sure we're just writing it correctly. If I have lined paper like you do, no, like you don't. If you have lined paper, this is all on one line, and this is written right below. Okay? This is all one line, this is written below. Okay, so verbally, what's happening over here verbally? As X is increasing without bound, as X is going, Y is decreasing without bound. That's your verbal statement, your words. Okay, so let's look at the next one, B. Give me the verbal for the left side. What is the left side verbal? As X is decreasing without bound, what's happening to Y? Y is increasing without bound. When something's going to infinity, the words we use are without bound. That means no stopping it. Okay, so that's the left verbal. What's the right verbal? As X increases without bound, Y increases without bound. So what will be your limit statements? Guys, this is always going to be the left one. X is going to negative infinity. That's left. And then your limit to the right. Okay, so what happens? On the left side of picture B, we are going up. Do you understand that notation? And on the right side, we are also going up. When you have an even degree polynomial, these will always match. Because don't evens always go like this or like this? But when you have an odd degree polynomial, they'll always be opposite. Perfect. All right, sketch a polynomial function with the given and behaviors. Now, there can be zillions of different answers, okay? But what we have to look at is what's happening on each end. That's the important part. What's happening on each end. So what does this first problem say? The limit as X approaches negative infinity. So over here, what's my curve doing over here? It's going down. Going down. These are polynomials, so no straight lines, just some kind of curve going down. What's happening on the other side? It's also going down. So you could just make it a parabola. I mean, that would be fine. You could also put some kind of weirdness in there. It doesn't matter as long as both of them are going down. Okay, now what about the next one? What's it gonna look like? Well, on the left side, we are still going down. But on the right side, we are going up. So I'm just going to put a couple of squigglies in there, and that would be an acceptable picture of that. Are you okay with that? Now, Mr. Passwater believes that it's easiest to find the end behavior on one side or the other. It doesn't matter. It doesn't matter. I don't find either side easier. I think he thinks it's easier on the right side because in a normal situation, evens are always going to end up, and in a normal situation, odds are always going to end up. So the right side will always be positive infinity unless, of course, you put a negative into your problem. So that part of it, I really don't care about that. I kind of cross that note off myself. The right side goes up if the leading coefficient is positive. The right side goes down if the leading coefficient is negative. That will always happen. I do not necessarily want you to memorize that, guys. you got too much crap to memorize. Just remember that evens are up, and odds are down, up. That's what you need to remember. As long as you remember that, life is good. The left side goes in the same direction of the right side if the degree is even. If it's odd, they are opposite. We talked about that a minute ago with the limits. They're both going to be positive infinity or negative infinity if it's even. All right, example 3. Take a second and determine the end behavior for the following polynomials. You don't need to write out all the limit notation. Just put down positive infinity or negative infinity. We'll practice our limit notation in the next part. So take a minute, think about those functions. Don't get your graphing calculator out. Try to do this just based on what you know about even and odd degree. Technically, for each of these, we should be writing our limit notation, but we're not doing that for this particular exercise. But that's what this is. The left side is the limit as x approaches negative infinity. Okay? Now, what do you think about that first one? What did you say? Did you say negative and positive? Because this is a 5th degree, it's an odd polynomial, and this is what odds do. They start down and end up. What did you say for B? Positive, positive, because it's a 4th degree. This is what it looks like. Now C, be careful, what did you say for C? Negative, negative, because it's an even degree, it's a 6th degree, and it's negative. So instead of up, it's down, down. D. Positive, negative, very good, because it's this upside down. What did you say for E? Same thing, it's basically the same problem. I hope you didn't fall for it. It's not in descending order, did you catch that? So the degree of the polynomial is actually 5. And what about the last one? Think about if you FOILed that out. How many x's would you have? It'd be x cubed, and wouldn't it be negative x cubed? So if it's a negative x cubed, isn't it positive negative? Isn't a negative x cubed the opposite of this? Oscar, you with me?
Yeah.
Okay, look like you're gonna yawn now for a second. All right, now we're gonna write limit statements. Your limit statements are always these. I always wish I had like a stamper that I could just stamp that on and not have to keep writing it over and over again. Those are your limit statements for your end behavior. This is left, this is right. So what are you going to say for example 4A? Come on, easy. Negative, negative, yep, so negative infinity, negative infinity. Why? Explain that, why? And the degree is even. So an even degree, negative coefficient is gonna have down, down behavior. Negative, negative behavior. Beautiful. All right, what about B? I'm just gonna list this here. What about B? Now think about that equation. Think about what's happening on the left, what's happening on the right. What do you think? Negative, positive, very, very good. Because it's a regular old cubic polynomial. Not complicated, right guys? Not complicated at all. All right, now, use a graphing calculator to determine the end behavior of the following functions. Now, I don't think you need a calculator for A. What shape is A? It's a parabola. So what, and it's a positive x squared. So what is the end behavior of a positive x squared parabola? Positive, positive. Yeah, that one's easy. Now go ahead and get your calculator out to do B. Because that one is not a polynomial, guys. This is gonna be funky. This is not a polynomial. Also, if you have an old school calculator like I have, when you put this in, make sure you're putting 2x minus 3 in parentheses and x plus 1 in parentheses. Okay, that's the way you're gonna have to put it in if you have an old calculator. If you have one of the new ones, they make fractions for you. I'd use regular Zoom 6 to graph it. Soon we're going to be graphing these by ourselves. Definitely funky. This picture has an asymptote, and some of the newer calculators are going to graph it beautifully. We have an asymptote at -1. Look at your problem. How come there's an asymptote at -1? Denominator can't be 0, so we're saying, okay, I can't be -1, so I put a wall there to stop the picture. Okay, and then it looks like it does this and this. Would you agree with that? Something like this is what you're seeing on your paper? Now, clearly, this picture is not heading to infinity or negative infinity. Your job is to decide what happens when we head off the page. So we're answering this question right here. We're finding those end behaviors. So what is the curve doing as it comes out this way? Can you tell? It's actually approaching an asymptote. You can't see it, but it's there. Look at your fraction and think about what happens as x gets really, really big. That's what's happening out here. X is getting really big, like a billion. This becomes 2 billion minus 3, and this becomes a billion plus 1. How significant, if x is a billion, how significant are these? Not. So basically the fraction becomes just about 2 billion over just about 1 billion, which is 2. So you have a horizontal asymptote at 2. There's a path on the picture, it's at 2. As we go this way, this is this one, as we go to the right, do you see that we are getting closer to 2? And we indicate that like this. Guess what that tells me? I'm getting closer to 2 from the bottom. Because over here, boys and girls, we're getting closer to 2, but we're getting closer to 2 from the top. And we want to distinguish that behavior. Because you know how I gave you statements like it's increasing, decreasing, maximum, minimum, and you had to come up with a picture? They're going to give you stuff like this, and you're going to have to come up with a picture. So this tells me the bigger X gets both directions, the closer to 2 I get. On the right side, I come up from the bottom, and on the left side, I come in from the... Okay? All right, one more. Try the next one. It is also going to have an asymptote, a vertical asymptote, because no way can X be 0. I'm getting something that looks like this. What are you thinking? Is that what yours looks like? Now, we are not surprised at all by this right here. We know we're going to have a vertical asymptote because X can't be 0 in this problem. Now, I want you to think, though, I'm really not concerned about this. I'm concerned about the ends because I'm doing end behavior. This is end behavior. So what happens as we head off the page this way? It looks to me like I'm getting closer to 0. Now think about that. That should make sense to you. Because if X is a huge number, like a billion, isn't this going to be negative 10 over a billion squared, which is just about 0? But notice, it's coming towards 0 from the bottom. So on the left side, our limit is going to be 0 from the bottom. What about the right side? Isn't it the same? 0 from the bottom. End behavior tells me what my graph does as it heads off the page. This tells me as X gets bigger and bigger negative, so as X decreases without bound, Y gets closer and closer to 0 from the negative side. That's what that says. You okay? All right, now I want you to go to the next page, the back of the next page. Check your understanding. Use limit notation. So the limit as X approaches infinity, and the limit as X approaches negative infinity. This one is the right side, this one is the left side. So look at your picture, that's easy. What happens on the right side? Positive infinity. What happens on the left side? Positive infinity. Okay, we must have an even degree polynomial, right? So is it possible for it to have a degree of 5? No. Because why? The end behavior matches, which means it must be even degree. Which of the following terms, when added to the given polynomial, will change the end behavior? Check all that apply. Okay, so look at the polynomial they gave you. It's negative x to the 7th. By the way, with end behavior, do I really need to know anything else? No, this is the key, right here. Now, all the rest of that junk is going to have impact on the graph, but not its end behavior. So this one looks something like this, right? With some other squigglies and stuff, but that's Everybody okay with that? All right, so what if I stick a negative x to the 8th on there? Will that change the end behavior? Absolutely, because then it becomes even degree, and then it's not gonna be one side up and one side down, so definitely that one changes it. What if I stick into the middle of the problem a negative 3x to the 5th? Nope, won't matter. This is the controller right here, that guy's in charge. What if I what if I add in a 5x to the 7th? Yes, because that will change my polynomial to be 3x to the 7th, which would be the upside down of this. So that one, check that one. How about if I add 1,000? Nope. How about if I add negative 300? Nope. The only thing that matters is this guy right here when we're talking about end behavior. All right, use limit notation to describe the end behavior of this guy. So it takes longer to write out the limit notation than it does to do the problem. Let's look at it carefully. If you timesed it all out, you would have x to the 3rd, and the coefficient on it would be positive. So what does a positive x to the 3rd look like? On the left side, negative infinity. On the right side, positive infinity. All right, last one, quickly. The graph of this thing has the same end behavior as what? Be careful. He mixed up the terms. What's the leading term in this problem? Negative 5x to the 6. So this is a down, down. Which other one has a down, down? B. That's it, B. So the answer is B. Okay, you feel like you got a grip on that? Guess what? You're going to do 1.6 due on Monday. Okay, you got the homework? Good job. You do not need to put the plus on the positive infinity.